You do. Sorry about that. All right, so let's double check and see. He's not here. Here we go. Taylor's on here, right? Does anybody have a question? First, let's talk about the ones out of the book. Okay, so you got some homework problems out of the book. So let's see if anybody's got a question on one of those first. All right, question 15. Number 15? All right, let's see what 15 says. All right, 15 says, all right, assume that the following patterns are built of square tiles and the pattern continues, so answer the questions that follow. Now, I'm not going to take time to redraw the whole thing. What I would do is this. Tell me how many squares are in the first video. How many squares are in that first picture on number 15? Everybody got your book open? Books have to come to class, books have to be open. Remember what I told you, you can have an electronic if you can get that electronic calculator. Okay? So make sure you bring your books every time. Okay, unless you have some kind of special accommodation. All right. So look at number 15. You're on page, you're like what, 31? Okay, so all books open to page 15, number 31. All right. So instead of drawing them out on the board, I'm just going to like write down how many squares are in. All right, so how many squares are in the first picture? Just how many? One. Just one. All right. Count how many squares are in the second picture. How many are in there? 5. All right, how many squares are in the next one? 11. All right, what about the next one? 19. All right, what about the next one? How many? Oh no, I hadn't counted them. How many are there?
29.
29. Okay. Now, here's what they asked me. What are they doing every time? I mean, they've got this one little square, and then this next time, they've got like this. And they've got one more, right? And then the next time, they've got like this. And then this, right? So what's happening every time when they draw the next picture? What's happening to that bottom one? All right, so it's getting one longer, right? Now, what's in this big picture right here, a square? Everybody with me? Like, that's a square that's 1 by what? 1. What's this a square that's what? 2 by 2. What's this going to be a square that's what? 3 by 3. What's the next one? 4 by 4, what? So I know the square is getting one longer every time. So, I mean, this is what I'm doing when I'm looking at it. So this square was a 1 by a 1. What was this square part? It was a what? 2 by 2. What's this square? 3 by 3. Now notice, isn't this the first one is a 1 by 1? And the second one's a 2 by 2? And the third one's a 3 by 3? What do you think the 10th one would be? 10 by 10. Now, is that all the squares that are in the picture? No, they got some on the top, right? Now, what happens? How many squares are on top of this picture? 0. How many squares are on top of that picture? 1. How many squares are on top of that picture? 6. Do you see a pattern? How many squares are going to be on top of the 10th picture then? 9. Now, when you're counting all the squares, don't you have to count these squares? The squares inside the square? And then what have you got to do to this on the top? You've got to do what with those two things? Multiply them, add them, what? Okay, y'all are talking how much math, you have to talk louder. What am I going to do with the squares that are in the big square and the squares that are on top? I'm going to have to add them. So I've got to add The square is kind of in the big square. And what am I going to do? I'm going to add those to the squares what? On the top? Everybody okay? Now, what's another way of writing 1 times 1 and 2 times 2 and 3 times 3 and 10 times 10?
1 squared.
You could have 1 squared and what? 2 squared and what? 3 squared and so forth. So if my square is n by n, it would be n what? Squared. Everybody okay? Now look what they asked on the first one. How many tiles are there in the 6th figure? Well, help me. On the 6th figure, how big would the square be?
6 by 6.
6 by 6. How many squares would be on the top of it? Right? Isn't that what's happening on all these? All right, look at what the second question says. How many square tiles then would be in the nth figure? Well, if it's the nth figure, how big is the square going to be?
N by n.
N by n, right? So we said that was n what? Square, but that's not all I have to do, right? What have I got to do to that square? Don't I have to add the tiles on the top? And what do we say the tiles on the top for? If it was 10, how many were you adding? 9. So if they're n, how many are you adding?
N minus
N
1.
minus 1. Are we okay? Now here's what it asks on the third one. It says, is there a figure that has exactly 1,200, what is it, 59 tile squares? If so, which one? Now, I'm confused. What's that 1,259 they're asking me about?
Total.
That's the total. Okay, did we just figure out how to get the total? Isn't this how we get the total? So I want to know, is this thing ever equal to what? To that. So does this ever equal 1,200 what? 59. Now, supposedly at some point you pass the state algebra test to get here. Okay, and quadratics are on the state algebra test. So do you remember, because it's probably been a long time since that algebra test, all right, do you remember how you solve quadratic equations? Because it might be on the praxis test. What do we do with quadratic equations? Help me. All right, what am I going to do before I factor?
Factor 1, 2.
Don't I need everything on one side? So I've got to get rid of this 1,259. How are you going to get rid of that 1,259?
Subtract it.
I want to subtract it. Now, do you understand that an equation is perfectly balanced? So if you do something to one side, isn't that going to mess it up? How are you going to get it to balance back out? You have to do it to the other side. So I've got this n squared plus n minus 1, and I've got this 1,259. So if I'm going to turn around and subtract 1,259 from this side, I've also got to subtract what? 1,259 from that side, do I not? So that leaves me with an n squared plus an n minus 1 minus this is going to give me a minus what? 1,200 what? 60. Does that thing ever equal 0? Now, when you go to factor it, back in algebra, you should have learned that if there's a minus in front, then that tells you that you have one of each. Like one's plus and what? One's minus. If there's a plus in front of the number, that means that these match. We're either both plus or both what? Minus. So I'm wondering, you know, do I know? Now, there are so many different factors of 1,260. Everybody with me? Now, I haven't worked this problem, so I don't know. Now, I know, but I do know that if the signs are different, I'm going to have to subtract them. So these two numbers are going to differ by how many? They're going to differ by 1. Is there a pair of numbers that multiply together to give me that differ by 1? I have to play with it and see. Now, if you have trouble with trial and error like here, what you can always do is the quadratic formula. Okay, if you do the quadratic formula, it's always x minus and x minus. Now, this is kind of a preview of coming attractions. All right. Now, another way of doing it is guessing and checking. Is everybody with me? you might jump way out nowhere. You think, well, I don't remember all this algebra. Like, well, maybe I'll do some guessing and checking. Because I don't know that there are a lot of fourth graders that are going to do the quadratic formulas. Everybody with me? So they might say, I'm going to what? I'm going to guess and check. All right. How many would be on the 10th one? What would that be? That would be 10 what?
10.
Squared plus how many?
9.
9. That'd be 100 what?
9.
9. Now, I need a number way bigger than 109, right? So maybe I try a bigger number. Maybe I try, what do you want to try? What would you jump to?
I started with 30.
Okay, so 30 would be 30 squared plus, well, how many would I have to add now? 29. Okay, what's 30 times 30?
900.
900. So I have 900 plus 29 is 900 what?
29.
Well, that's a lot better than my 100 what? 9. So what might you jump to? You might jump to 31 or 30. Everybody with me? Now, suppose I jump, to show you something, suppose I jump to 33. Okay, you got a calculator. Figure out what 33 squared is for me. Or do it by hand. I don't care. But find out for me right now what 33 times 33 is. Either with by hand or with the calculator. So, always bring the calculator or bring it. All right, what's 33 times 33?
1089.
1089. Now, what am I going to have to add to that 1089?
32.
32. All right, so add that for me and tell me what I get. That's 1001.
121.
All right, now I'm getting a lot closer, aren't I? Try 35 squared. What's 35 times 35?
1221.
1200 what, 25? All right, what would I have to add to that? A what?
34.
A 34. So what's that going to give me? 1,200 what?
59.
Oh, is that what I needed? Now, I know enough arithmetic and algebra that I could go back and either use the quadratic formula or I could go back and do trial and error to figure this out. Is everybody with me? But if I'm in the 4th grade, I don't know either of these, right? And if it's been a long time since I had algebra, I don't remember. Is everybody with me? So look what I did here. I used a lot of problem solving techniques. So the first thing I did was I looked at the picture, drew the picture, they gave me the pictures. Everybody with me? Then I looked for a pattern. Isn't that another problem solving strategy? But I looked for the picture, I looked for the pattern from the picture. Everybody with me? Then we ended up doing some kind of some guess and check after we got kind of a pattern. So a lot of times when you're working these problems, there's not just one problem solving strategy, there's a bunch of problem solving strategies. And writing an algebra equation is cool, but sometimes it's too much trouble. Sometimes there's not an algebra equation. And if you're in 4th grade, there's really not what? An algebra equation. Okay? So everything in life doesn't have a quick answer. So everything in school doesn't need to have what? A quick answer. So part of your job as a teacher is you've got to get your kids ready for the real world. So a lot of times, the problem we talked about before is kids think that if a problem can't be solved, they don't know what to do immediately, they don't know how to work it. Well, first of all, that's not true. But a lot of times in school it's true, because that's what the teacher does. She gives them one that looks exactly like what the other one looks like. Okay? But we talked about in class the difference between a problem and an exercise, haven't we? What's an exercise solved with? An algorithm. In the real world, most problems don't have algorithms. Okay? So we kind of got to get used to the problem solving idea. Okay? Or anybody else got a homework question on the book first? All right, what about the worksheet? Pull that worksheet out. Okay? Now, did you figure out what was happening on number 1? What's the pattern? What's it doing every time? Just what?
40.
It's just flipping between some numbers, isn't it? 4, 0, 6, what? 406, it just keeps repeating the same number, so what go in the blank?
4064.
640 what? 640, is everybody with me? Now, did you figure out what's happening on number 2? All right, somebody tell me what's happening if you figured it out. What's it doing every time? It's going one more, isn't it? Think about it kind of like going upstairs. It goes 3, 4, then it starts back over and goes what? 3, 4, what? 5, then it starts back over and goes what? 3, 4, 5, what? 6, that's the first number that you're missing, right? Then it's going to start back over and go what? 3, 4, 5, 6, what? 7. But if anybody find a different pattern? Now see, neither one of those are those arithmetic or geometrics. Everybody with me? It's just a pattern. It's just something you're noticing. All right, did anybody figure out number 3? What's it doing? Could you figure it out?
Counting up and then counting down.
Yeah, it's kind of like it's going up the stairs and back down the stairs. So it goes from 1 to 2 and then back down to what? 1. Then it starts over and goes one more, doesn't it? So it goes 1, 2, what? 3, and then back down what? 2, 1. Then it's going to start over, and it always goes one step higher. Is everybody with me? So it's going to go 1, 2, 3, 4, and then back down 3. So what goes in the blank? 2, and then what? 1. And then it starts over again. So it goes 1, 2, then what goes in the blank? 3, 4,
5, 4,
then it's
3.
gonna what? Come back down, 4, 3, and then there's your 2. Now, all of these are not, to me, the first ones were harder than the next ones. So you got a lot more practice on arithmetic and geometric than you do just different kind of patterns like those. What's happening every time on number 4? What's it doing every time? Adding 3. So what goes in the blank? 14, 17, what? 20, 23, and 26. All right, when it's adding the same number every time, what's that? What kind of sequence is that called? That's that arithmetic. Okay. On number 5, what's happening every time? It's adding 5. So what goes in the blank on number 5? 28, 33, 38, 43. Everybody with me? Okay, that's arithmetic. Now, what's happening on number 6 every time? Is it going up or down, first of all? Going down. Is it going down by the same amount? What's it going down by every time? 7. So every time they're subtracting 7. Now, is that an arithmetic sequence? Yes. Remember we said you could be adding the same number every time or what? Subtracting the same number every time. All right. On number 7, though, here's what you have. You have a 2 and a 4 and a 7 and an 11 and then a blank, 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 and what, a 56? Now, are you adding to get to the next number every time? Okay, somebody's saying yes, somebody's saying no. If you're saying yes, tell me, what am I adding? Am I adding the same number every time? No. What am I adding to get from here to here? 2. Then what did you add to get from here to here? 3. What did you add to get from here to here? 4. So what do you think you're going to add now? You're going to add a what? 5. So when you add 11 to 5, what went in that blank for you then? 16. Then what do you think you're going to add the next time? 6. So what's that going to get you? 22. And then you decide you're going to add 7 and get a what? 29. And then you probably added what? 8. And what's that going to get me? 30 what? 7. And then sure enough, if you add 9, you end up getting 56. Yeah. Did anybody find it different? Now, is that one called arithmetic then because I'm adding? Why? For it to be arithmetic, you've got to be adding what? The same exact number every time. Okay. All right. Can anybody figure out number 8? What'd you do?
I did 5 numbers.
Okay. All right, so 4, 7, 12, 19. All right, so Amber, tell me what you got in the blanks.
28, 39, 52, 67, 84, 102.
All right, so does everybody agree with those two? Are we okay? All right, Abby, when you said adding odd numbers, what you meant, like when you added this, you added
I did 3,
3 and then
5,
5 and then
7,
7. So you thought, well, I bet that's gonna be what? 9, and that's how you got to 28. And then you 11, is everybody with me? So she saw it as adding odd numbers. Anybody see it as doing it any differently than that? Okay, let's skip over 9 for a second. Okay. 10, what do you do every time on number 10? Are you multiplying? What are you multiplying by every time? 2. Now some kids don't see it that way. They see it as adding to itself. Is everybody with me? So some kids will see it differently. So if you're multiplying by 2, what do we call that when you're multiplying by the same number? Geometric. All right, look at number 11. What do you do on number 11 every time? Dividing by 3. So what's in your blank? 9 and then what? 3 and then 1. Now in that next blank, you better not have 0.3. You wouldn't get any credit. That's 1/3. Is everybody with me? And in the next blank is going to be what? 1/9. Rounded off decimals are not the same thing. Sometimes fractions can be decimals, but they've got to be exact. Okay? Now, most of my students usually struggle with number 9. All right? So let's see what we've got. Got 2, 3, 5, 5, 8, 7, 11, blank, 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 17, blank, blank, blank. All right, does anybody figure out something to put in the blanks? All right, tell me what you got. What should I put in those blanks, Abby?
I have 9, 14, 11, 13, 20, and 15.
13, 20, and 15 right here?
Yes, ma'am.
All right, tell me what you did to get, does anybody else get those numbers? Okay, several of you, okay? Tell me, Abby, what did you do to get them?
So I found that every other pair is different. So the first two you're gonna
So in
start,
other words, you're looking at like this number, like that?
like the 2 and 3, they start off with adding 1.
Okay,
That's plus 1.
okay,
So then the 3 to 5 is plus 2.
okay,
But every other number is different. So the first, like the plus 1, that set's gonna start subtracting. And then the plus 2, that's gonna start adding. So the next number I have from the 2 to 5, I mean, not the 2 to 5, the 5 to 5, that's plus 0.
okay,
So then the next one is plus 3.
okay,
So you see, like it goes 2, 3, so that's counting up. Then the 1, 0 is counting down, so it goes 1, 0, -1, plus 4. Does that make sense?
I think so. So here what happened?
That's -1,
Okay, and then here was what?
plus 4.
Okay, so how did you get the 9 in your head? I mean, what did you do to get the 9?
I subtracted by 2.
Okay, so you were looking at, let me make sure I'm clear. All right. So you glanced down here and said 1, then you skipped over and went
Yes, ma'am.
0, and then you skipped over and went
-1,
-1. So then you skipped over and went
-2.
-2. You see what she did? All right. Did anybody else get the same answer a different way? All right, tell me what you got, Annika.
So I looked at the ones you boxed,
Okay.
like the 2, 5, 8, and 11.
All right.
For those ones, you're adding 3 each time.
Okay, so you kind of went like this.
Yeah.
All right, so if I add 3, that would get me the what?
14.
The 14. And if I add 3, that would get me the what? 17. And if I add 3, that would get me the what? 20. All right, so you saw it different than Abby saw it. Okay, well, let me ask you this. So, Abby, then you went to these numbers and went, all right, so you went 2 and then 3. So you're going up by 1 every time, right?
Yes, ma'am.
So 2, 3, 4. So then you went up by
5.
5, and that's how you ended up getting that number. is that right?
Yes, ma'am.
All right, how did you do it then, Annika?
So then the other ones, the 3, 5, 7.
All right, so the
9,
ones that are on box 3, 5, 7,
9, that's the other
so it's
pattern.
the other, so you saw two different
Yeah.
patterns. So you look at these numbers as separate than those numbers, all right? But Abby looked at them kind of as separate things, but you did it differently, okay? But either way, you get those same answers in the blank, is that right? All right. Did anybody else get different numbers in the blanks? All right, let me show you something. I've seen a student do this before. Those go up by 1. Those go up by what? 2. What do those go up by? 0. Kind of like Abby was doing. Those go up by what? 3. What's that go down by what? 1. And that one goes up by 4. And then they just start it over. So what's the next gonna go up by? 1. So that would be a what? 12. Then go up by what? 2. So that's going to be a what? 14. Then go up by 9. So what's that going to be? 14. Then go up by 3. And sure enough, what is it? 17. And then go down by 1. So what's that going to be? A 16. Then go up by 4. So that's going to be a what? 20. And then start back over. Go, you see what I'm saying? Now, is that going to be the same numbers in the blanks? Does it work? Yeah. Now, once somebody blew my mind all the way up. Because she did this. And never did I see this. What do those add to? What do those add to? What do they add to? What do those add to? 5 what? 10 what? 15. So right there, you know what she had in that blank? A 9. Because she expected that pair to add up to what? 20. Then, what did she make that pair add up to? Now, what two numbers? She just grabbed a pair. You see what I'm saying? She could have put 20 and 5. She could have put 21 and 4. She could, you see what I'm saying? Like, then she made this pair add up to what? 30. Is everybody with me? And she made that pair add up to what? 35. Whatever. Now, I guarantee you that the key had one of these, probably that one. But isn't that a beautiful, I've given this worksheet out for 10 years and never noticed it. Those added to 5, those added to 10, those added to what? You with me? So sometimes there's more than one right answer. But you've got to be careful when you use materials that come from somewhere, because they're going to come probably with a key. Just because it comes with a key doesn't mean the key's right. It also doesn't mean the key's all the things that are right. So when a child gets a wrong answer, one thing you have to be real careful about is ask them, how'd you get that? Because it may be, now, every number's not right. I mean, sometimes it's like they can't tell you why they wrote down 4. It's just like, I like 4. You know what I'm saying? Like, they didn't have a valid, logical reason. But if they can articulate a pattern that they see, and they follow that valid pattern that they see, are they right? What's the answer? Yes. So all patterns aren't the same, and sometimes they're the same, like Abby and Annika have, but they don't see them the same. But they get better at them by doing them. But you've got to be real careful when you're the teacher, and here's what I mean. All right. When my daughter was in kindergarten, she got in the car after school one day in the spring. and she just burst into tears. Ooh. Now, if it had been my son, it'd have been a regular day. Okay. My son was my EKG child. Kelly, this is happy, this is sad. You know what I'm saying? She's just a real laid back, even kid. So for her to get in the car and just burst into tears was like, what? And I said, what in the world? And that little 5-year-old sobs, I can't act. And I said, what? She goes, I can't act. She's shrieking. And I said, why in the world do you think you can't act? I missed every problem on my worksheet. Now this is a kid who usually got every problem right. You see what I'm saying? So I said, okay, wait, it's okay. We'll figure it out. You know, take a deep breath, do some exercises. Let's go get something to eat. You know, food cures everything. Okay. So we go home and she gets her snack, and she's got her milk or her cookies or whatever. And I said, can I see your worksheet? Ooh, start again. You're like, have another cookie. Let's start that eating disorder. Have another cookie. Okay. So she's calmed down over here, munching on some sugar. Okay. And I pull her worksheet out. Now, understand, I adored her teacher assistant. Her teacher assistant was fabulous. But unfortunately, in this instant, what she had done was this. Sure enough, Kelly had missed every problem on the worksheet. And her teacher had erased all Kelly's wrong answers and written the correct answer so Kelly could study. Is everybody with me? Now, luckily for me, I could still read a lot of Kelly's answers that were erased. Now, they would be like this.
Oh, that's cute.
Can she add?
Yeah.
What? What's she doing?
She's adding the number.
She's adding all the numbers. She's not saying that's problem number 1, so 3 plus 8 is 11. Kelly's going 1 plus 3 is 4, and 4 plus 8 is 4. You see what I'm saying? Can she add? Oh, yeah. Now, it would have saved me a whole lot of stress in my house, and I'd have more cookies by myself. You see what I'm saying? If the assistant had just looked at Kelly and said, what? How'd you get that? And then Kelly would have said, well, 1 plus 3 is 4, and 4. So I just told Kelly, this, because you've never seen it written that way. I said the first number with the dot after it is problem number 1, problem number 2. They don't want you to add those numbers. So circle the number in front of the dot and don't add the number in the circle. Problem solved. So when you got kids, you need to ask them a lot of times, how did you get that? But now, don't just ask them, how did you get that, when the answer's wrong. Because if you ask them, how'd you get that, and it's only when it's wrong it becomes code for, hey, stupid, why don't you try again? Do you see what I'm saying? So you've got to get in the habit of asking kids, how'd you get that? How'd you get those numbers in the past? How'd you get those numbers? Now, the other thing is this. I've been teaching for decades. Some things about children and about students, whether they're children or adults, are the same, and some are different. Here's what's different about your generation than the generations I've had in the past. I do not know why, but y'all seem to be much more anxious about making a mistake. My guess is your parents didn't let you do that very much. Or teachers got on to you. You see what I'm saying? So you're very nervous about getting something wrong. Like the thought of going to the board and putting it up there and it being wrong, like your life would be over. Whereas that was just the way we learned. You see what I'm saying? And I need you to understand that that's the way most people learn math. You get it wrong before you get it what? Right. So when a kid's getting it wrong, they're going the right way. So you got to make it safe in your room. to be wrong. That means you tried. You see what I'm saying? You've also got to teach kids this idea of exercises versus problems. We already talked about that. So when a kid just has a meltdown in your room and says, I can't do it, I can't do it, don't look at them and go, yes, you can. Because you just called them a liar. You see what I'm saying? They know. They tried and what? It didn't happen. So you teach them one word. Yet. I can't do it what? Yet. That's different than what? Then I can't do it. So when they start crying and having, I can't do it yet. Because that validates if they are struggling, but it gives them hope that that struggle is not going to be their permanent state. Is everybody with me? And everybody struggles at something. So I can't do it yet. But sometimes you have to do it wrong 14 times before you get it right the 15th time. So you know that one wrong time means that's one less time you're going to get it wrong. Isn't that great? You're going the right way. But it's got to be safe. So you can criticize ideas, but you can't criticize people. All right? Answers can be wrong, people aren't. You see what I'm saying? So you've got to make it safe where they're, so give them things that don't have any answers. Give them things that have multiple right answers. Give them things you know they're going to get wrong before they get, it's got to be safe for everybody. Okay? So it's got to be safe for you. Now, give them problems that aren't so straightforward. I want problems, not just exercises. All right, don't tell a kid, when you see total, you add. Because I might say there's a total of 14 balls and John has 6. How many does Andrew have? You see what I'm saying? Just because the problem has the word total in it doesn't mean you automatically what? Add. Now what you can say is if you see the word total, adding comes to, it's a possibility. But on standardized tests now, they're getting away from these code words, trying to make sure that the kids can read. They're also beginning to give them problems. But you can give them problems that are simple. For instance, what if I told you this? Your yard on the backyard is 15 feet across your backyard. And somebody has given you some fencing, okay? But you have got to go down to Home Depot and buy the post. Is everybody with me? But you're going to put a post every 3 feet. So it's like a chain link fence. All right, so you have a post every 3 feet, and it's 15 feet across the back of your yard. How many posts should you buy when you go to Home Depot? Well, somebody be brave and tell me how many posts you think that you would have to buy when you go to Home Depot. 5. But it's not right. What's the first thing you got to put? What's the first thing you got to do when you go to build a fence? You got to put down a what? A post, don't you? Doesn't the fence have to start with a post? And then you go for 3 feet and put another what? Post. And then you go for what? 3 feet and put another what? Post. And you go for 3 feet and put another post. And you go for, everybody with me? Well, so far I've got 3, 6, 9, 12. Everybody with me? That's your 15 feet. That's your 5 posts. What's your problem? You've got some chain link fence swinging in the breeze. You have to have another one at the end. Now you got to drive all the way back home, Depot. That's really inconvenient. You see what I'm saying? So it's not a hard problem, but it's not, you grab the 2 numbers in the problem, the 5, 15, and 3, and do something with them. You see what I'm saying? So you need to kind of get into practice doing that. So on your part of your homework is going to be, I'm going to give you a few real, what I call problems for you to kind of just play with. They're not really hard. They're just not, you're not going to solve them with an algebra equation. Okay? All right, so that kind of finishes kind of the problem solving part.
Okay, I found a really quick question when I was looking. In the book on 2D, it goes from like 10 to the 9th, from 10 to the 11th, from 10 to the 13th. And I said it was arithmetic because I was just adding 2 to the exponent. But it's geometric, so I'm confused.
Okay, which number is it that I'm looking at on which page?
2D.
2D. All right, so 10 times 10 to the 3rd times 10 to the 5th times 10 to this, that one. Right here's why. That's a very good question. Everybody with me? Let's talk about what exponents are. What does 10 to the 3rd mean?
We're multiplying the same as 3 times.
Right? All right, what does 10 to the 5th mean? Right? What does 10 to the 7th mean? How many of them do I have?
7.
So what's the difference between this number and then this one, of course, is just 1 10. Is everybody with me? So what's different from 1 to 2? They both have a 10, right? But this one took the original 10 and multiplied by that. What is 10 times 10? It's 100. Is everybody with me? This has 3 10s. That has how many 10s? 5. So there's your original 3. Again, what did they add? They multiplied by another 100. Is everybody with me? And the same thing here. They had their 5th one, and they multiplied by another couple of 10s. Everybody with me? So really, what are you doing every time? You're multiplying by 100. So when it's arithmetic, it's got to be, you have to be actually adding a number to this number to get that number. You were adding, but you were adding to the power.
Right.
Right. But I want you to notice, most kids would see it as I'm what every time I'm adding. So that's why it's really important to understand you're adding to this term to get that term. In other words, the number that's the answer. Does that make sense? So I have to be adding something to 1,000 to get 100,000. I've got to be adding something to 100,000 to get 10 million. Okay. Or any other questions before we go on? All right, now what we're going to do is we're going to start chapter 2. Now I'm going to kind of, I wish I could go over section 1 on logic, but we just don't have time to do that. All right, so we're going to start in this section 2 too. Okay, so we're going to be talking about sets. Now, like I told you kind of that first day, sometimes in Math 210, the hardest part of the class is the beginning. Because real problems, you're not used to real problems, you're used to exercise. So it freaks you out when you read something and you don't know the right answer right away. And like I said, adults around you, we've done you a disservice, okay, by not letting you struggle again, okay? So that idea of productive struggle is really important, all right? So when a kid is struggling, don't always rescue them. Instead, you need to empower them, and there's a difference. Because they need to learn to do things themselves. You don't need to do it for them. But it's got to be age appropriate, and it's got to be like level appropriate. Because just because the kids are the same age don't mean they're capable exactly of the same thing. Okay, there's this idea of equity they're going to talk about in their education classes. So what's right for Annika may not be right for Abby, may not be right for Nav. Am I with me? So you got to know your kids really well. Now, what we're going to talk about next is something called sets. Now again, depending on your math background, most people didn't have a lot of experience with sets. They should have, but they didn't. Now, sets are just a collection of objects. I mean, it can be teddy bears, numbers, letters, I don't care. But a set's just a collection of objects. Now, an element is an individual member of a set. It's an individual member of a set. All right? So I could have the set of Math 210 students who come to class on Tuesday. All right? And if I did that, then Lauren would be an element of the set. Taylor would be an element of the set. All right, Katie would be an element of the set. Everybody with me? So just one person is an element. All of them together or make up the set. Now, I want to talk about ways to name a set. Okay. Now, one of the first ways is you can use something called description method. Now, this is usually the first way that anybody learns to name a set or describe a set. And what it means is you literally use words. Now, let me give you, you literally use words. But you've got to make sure that your words are very specific. They can't be vague. Okay? Like I can't say the set of good-looking people in this room. Because that's opinions. Everybody, we'd all be in it, but you know what I'm saying. I can't even say the set of blonde-haired people. Because what I call dark blonde, you might call light brown. You see what I'm saying? So if you're going to use description, it's got to be very specific. There can't be any vagueness to it. Your book calls them, it's got to be a well-defined set. There can't be any question on what's in it and what's not in it. So an example would be something like this. The counting numbers less than 5. The counting number is less than 5. Now, if I go to start counting the desks, what's the first number I start with when I count? 1. Then what do I say next? 2. Everybody with me? Those are the counting numbers. So is the number 8 in my set? No, but it's a counting number, but it's not what? Less than 5. Is 3 in my set? Yeah. Is a half in my set? It's less than 5, but it's not a what? Counting number. So as long as you understand the vocabulary, there's no question about whether something's in my set or what? Not in my set. Now, by the way, make sure you write this in your notes just because I'll use these two terms interchangeably. The counting numbers are exactly the same thing as natural numbers. So in a test, instead of saying, I want the counting numbers less than 5, I might say I want the what? Natural numbers less than 5. So what's my first natural number? 1. Everybody with me? Now, there's another set called whole numbers. Now, whole numbers don't start with 1. You know what whole numbers start with? 0. Think about a whole. Is everybody with me? So the natural numbers, the counting numbers are almost exactly the same set, except the whole numbers have one more number. So the whole numbers would be like 0, 1, 2, 3, 4. Or the counting numbers would be 1. Everybody with me? Now, here's a second way that kids learn to describe. Roster method. Now, this one's the one that we're going to use the most in here. All right, roster method. Some books call it listing method, but mathematicians are going to be roster method. Now, how do you do roster method? You actually list out all the members of the set inside of braces. Okay? So you list all the elements. Remember the things that are individual things in the set are called elements. You list all the elements in the set inside braces. Now, braces are those things that nobody can draw very well. Okay? That's a brace. Okay? What do we call this thing? Parentheses. What do we call that thing? A bracket. So these have to be, you can't do anything, it's got to be a brace. All right, let's do the same thing. What's the first counting number? 1. What's the next one?
2,
2. What?
3.
3. Do I put 5 down here? The counting number's less than 5? 5 is not less than itself, is it? So you understand that this and this are exactly the same set. It's just one is description and one is roster method. Okay? Now, sometimes we get into trouble though. Okay, we'll talk about it now. Okay, flip this over here so I can see this board so I can write it down. All right, what if instead I wanted the list of all the counting numbers? Can you possibly write out all the counting numbers like I did right here? Why not? It never ends, does it? All right, there's two things you need to understand. A finite set, and that looks like it's infinite, but it's pronounced infinite. All right, a finite set, the number of elements can be expressed as a whole number. Okay, the number of elements can be expressed as a whole number. So what that means is you could actually tell me exactly how many things would be in that set. Now, what's the prefix IN mean? If you were incompetent, what's that mean? You're incompetent. You're not competent. So infinite means not what? Not finite. Okay. So here, the number of elements in the set cannot be expressed as a whole number. Now, don't tell me you can't count them. Oh, you can count them. The problem is you never stop counting. Everybody with me? Now, it doesn't mean a really big number you don't know. I mean, most people know the number of desks in this room is finite. I start counting and end up with 32. So I counted them. 32 is a whole number. Boom, I'm finished. It's a finite set. What if I said this on a test? Is this finite or infinite? The number of hairs on your head. Is that finite or infinite? The number of hairs on your head. What do you think? It's finite. If you're really strange, you just take your hairs individually and start plucking them and counting. Is everybody with me? There would come a point where you're bald. Is everybody with me? Now, you might not know what to call that number. Is everybody with me? And once most people get that past trillions, they're kind of out of words. But there are words, you just don't know them. So while it's a really big number you don't know, it's still like what kind of set? A finite set. If I said the number of grains of sand on the planet Earth at this instant, that is still what kind of set? Finite. Well, little kids think infinite means a big number I don't know. And it doesn't. Infinite means no end. Is everybody with me? So here's the problem. If I told you to list the natural numbers by roster method, we'd be in trouble. Because I know what to start with. What does it start with? 1, then what? 2, 3. What's the problem? It never stops. So in math, what we do for never stops are what called ellipses. It's 3 dots. Dot, dot, dot. All the ellipses mean is the pattern continues. So that would be a way to write the natural numbers. If I just wrote natural numbers, that's description method. Do you understand that this would be roster method? Now, what if I was in a really bad mood in the test and I told you to list me the natural numbers less than 1,000? Can it be done? What?
Yes,
Do you want to do it?
absolutely.
No. So I would do it this way. 1, 2, 3, 4, 5, dot, 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 1,000. All the dot, dot, dot means is the pattern continues. That's all it means. So this would say that you can't just go like this. You can't go 1, 2, dot, dot, dot. Because I don't know what the pattern is yet. Because I might have multiplied by 2. Is everybody with me? Or I might have added 1. You see what I'm saying? You have to have enough numbers so the pattern is very clear. But this says, okay, the pattern is very clear. That says continue the pattern forever. What does this say? The pattern's clear, continue the pattern until you get to what? 1,000. So just seeing the ellipses doesn't make it infinite. Is everybody with me? This set is infinite, but this set is what? Finite. All those ellipses mean, they just mean the pattern what? Continues. Okay? So that's kind of the difference between roster and description. Now let's talk about this third kind. Now this third kind you don't see very much in elementary school, but you see a lot in middle school and high school. And it's called set builder notation. Set builder notation. Now it's kind of weird. It's a little bit like a combo of the other two. Now here's what it always looks like. Let me give you an example. Now, you write that down, and I'll tell you what that means. All right, you see it a lot in pre-algebra and algebra. Now, here is what this means. There's always this bar. To the left is what's in the set. And to the right is the rule to build it. Now, this bar is always read as the phrase such that. So I'm going to show you some terms. Now, in mathematics, we tend to use a lot of symbols. Now, we're really not being ugly. The thing is, these symbols are universal. They're not just American symbols. Everybody with me? So I can pick up an article from a German magazine that's a math thing, and I can follow it. Because since we don't use a lot of words, we use a lot of symbols, and the symbols are universal. There's no translation that has to happen. So we really do have our own language, which is good and bad, okay? It tends to intimidate people, but don't let it intimidate you. All right, you see this funny looking E? That funny looking E stands for element. So instead of writing the word element out, they just do that curvy looking E. So let me show you something. Remember what I said an element was? An element's a member of a set. Is A an element of that set? Is A a member of that set? Yes. Yeah. That'd be a true statement. Is A an element of that set? No, it'd be what kind of a statement? False. Now, sometimes instead, they'll just do it this way. What do you think it means when they put a slash through it? No, A is not a member of that set. That's what? True. True. So instead of writing out the word element, they just use the little symbol for element because it's shorter. Now, can you guess what that capital N stands for? Natural number. So when you see a capital N, a lot of times it'll stand for natural numbers. Look what this says. I want all the things, I want all the x's, such that those things have to be what? Natural numbers. So the things in the set have to be an element of the natural number. So is a half going to be in there? What? Is -4 going to be in there? Is everybody with me? And those things have to be, what's that? What symbol is that? Less than 5. So this says exactly the same things all those other things have said. Put all the things, the X is kind of the things, in the set where those things are natural numbers and those things are what? Less than what? 5. Now let me show you a different way that they'll do it sometimes. That looks real algebra. Super simple. First of all, I'm going to build this set. Everybody with me? What goes in the set? X's or N's? Remember, what's to the left is what's in the sets. Everybody with me? So what's going to go in the set are the what? The X's. Well, this tells you how to make the X's. It says take the little n's and double them and add 1. Well, what are the little n's? Now that says an element of W. Can you guess from over there what W stands for? Whole number. So do you understand that the n's are going to come from 0, what? 1, 2, everybody with me? All right, well, how do you get the x's? You take the n's and do what? Multiply by 2 and what? Add 1. So the first time, n's going to be a 0, right? What happens when you double 0 and add 1? What do you get? 1. Because see, your x takes your n and doubles it and adds 1 to it. Everybody okay? Then the next time, what's going to happen? It's going to take the next ones. Everybody with me? And what's it going to do to that one? It's going to double it and what again? Add 1. So what's going to happen now? What's going to fall out? A 3. Then, to get the next x, it's going to take the next n and double it, and what again? Add 1. What's going to fall out? Everybody with me? In other words, it tells me how to build my set. Now, does this set ever stop up here? Do these n's ever stop? So are these ever going to stop? So what am I going to put to show that? So don't let this set builder intimidate you. Now, you're not going to see it much in the elementary, but you might see it on a practice test. Everybody with me? But get kids to understand. Don't let them be intimidated by symbols. Now, here's the other thing. I'm going to talk about this a lot later. I'm big on, I do not want you to give them cutesy things. Now, what do I mean by that? Here's what I mean by that. In an effort to be helpful, I guess, here's what teachers will do. They want the kid to learn whether to put less than or greater than in there, right? But instead of teaching them which picture is which word, how were you taught to get the correct answer?
An alligator eats the bigger number.
Yeah, the alligator is that big old number. Now what they gonna do? You see what you did? The teacher didn't mean to do that, but he or she hurt you. And here's why. When you're in 2nd grade, the alligator eat the bigger number works, right? And if you're the teacher, you never leave 2nd grade. So you made your life easier. But they leave second grade. And they're gonna get to 7th grade where the alligator and the bigger number now what? It's not gonna work anymore. So what you cannot do with children is you cannot give them a cutesy little trick that makes your life easier and hurts them later. Now, Father's Day came this year, and I got a message on Facebook from one of my former students that's a teacher now. And she said, Dr. Gann, you're gonna die. She said, that gator failed him again. And she was behind somebody in traffic and took this picture and sent it to me. That's what was on the back of their SUV, and like they've written it like shoe polish. What's that say?
My dad is listening, Dad.
That's it. I hope they meant my dad's what? Great, the gator failed him again. They've got to learn that this thing has a name. It's called what? Less than. And this thing has a name, and it's called what? Greater than. Just like they learned your names, everybody with me? They can learn this thing's name. They grew with that. That's the picture of the dog. They're cool with that. They can learn names for things. So we're going to kind of nix those cute tricks. Now, there are 3 ways to name. With set building, I expect you to be able to name things all 3 ways. Now let's talk about these 2 ideas of equal sets and equivalent sets. Now, one of the things that's hard sometimes in a math class is sometimes words outside of a math class mean something different than words inside of a math class. So outside of a math class, equal and equivalent may be synonymous, but they're not synonymous in a math class. Equal sets have exactly the same elements. Equivalent sets have the same number of elements. And those are not the same thing. So if I ask you if the sets are equal, I'm asking you, do they have the same things? If I'm asking if they're equivalent, I'm asking you, do they have the same number of things? Okay? So does everybody understand these 2 sets are equal? Don't they both have an A? They both have a B, and they both have a what? A C. I didn't say the order had to be the same. I just said they had to have exactly the same what? Elements. Now, is that true? Does that set equal that set? No. But is this true? Are those 2 sets equivalent? Yeah. Why? Because this has 3 things in it. What? That has 3 things in it. Now, let me teach you another phrase. Cardinal number. Cardinal number is the number of elements in a set. Right, you see this set right here. What's the cardinal number of this set? 5. Now, you're going to learn in education about something called DOK levels, depth of knowledge. Okay? There are other things that talk about different kinds of ways when you test a kid. I get too many teachers outside in schools think that depth of knowledge means harder. It doesn't. Depth of knowledge means what are you using to solve the problem? What are you using to get the answer? So here's what I mean. When you start, we'll talk about this later, the very kind of tip of the pyramid is what they kind of call synthesis. You're putting together things in new ways that nobody's put together for you. That's different than a knowledge question. A knowledge question would be regurgitate back to me what I just said. In other words, memorize it. It would be, what is the quadratic formula? What is 2 + 3? Is everybody with me? Now, let me give you a synthesis question that's simple. What if on a test I said define equivalent sets using the phrase cardinal number? Because I didn't define it that way. How did I define equivalent sets? I said it's sets that have what? The same number of elements. So if on a test I just said define equivalent sets, that'd be the lowest level. That's just knowledge. You can just memorize what I told you and not understand. But instead, I can make this a much higher order thinking question by saying define equivalent sets, but you must use the phrase cardinal number. How would you define equivalent sets using the phrase cardinal number? You tell me. What are equivalent sets? All right, but use the phrase cardinal number in
We have the same cardinal number.
there. They're sets with the same cardinal number. See, if you understand what I said and you understand what I said over here about cardinal number, those are two things that are easy to put together. So it's not a difficult question, but it is a higher order what? Thinking question. All right? So equivalent sets, cardinal number. Now, these braces are kind of hard to draw. So a lot of times, if I've got to talk about the same set, like ABC, over and over and over, they will name them with single capital letters. Like it might be M is the set 1, 2, 3, 4. And N is going to be the set 0, 10, 20. So sometimes they will name sets with a single capital letter. All right, now in your homework, you're going to have to do a lot of reading, and the next time we're going to put the sets together. So first thing you have to do on page 51, it goes back and talks about like roster and set builder and description. Then it talks about equal sets and equivalent sets. It talks about something being in a one-to-one correspondence. Now, a one-to-one correspondence means everybody's got a partner. So you understand if you have two sets, for you to be able to pair them up, what do they have to have the same what? Cardinal number. What do you think an empty set is going to be? A set with what? Nothing in it. And there are going to be two symbols for it. You can either literally draw braces with nothing in them, or you can put a 0 with a slash through it. Either one of those are proper notation for an empty set. Where's your homework going to be? It's always on Moodle. Okay? All right, come see me if you need some help. I will see y'all next time. Oh, Zoom. And I will see my Zoom in here.